All right, hello and good evening to the three of you that are here. So me makes four. Um, uh, yeah, I don't have anything planned for tonight. I haven't received any emails, so I am open and available to answer any questions whatsoever. Kate, I know you're here, and a couple other people, if you're in my lab section, I know you were asking about the fourth electronic experiment. I haven't looked into it yet, mostly because today my wife was working, which means that outside of streaming, I have been living my life in 2-year-old land. So I haven't had a chance to look into it, but I can totally do that right now. And in the absence of questions, I'm going to check that out, get to the bottom of it. Of course, if you have questions that you want answered, things you want done live, I'll totally prioritize that. But in the absence, that's not a word. In the absence of questions, I'm going to check out lab experiment 4. Kyle, let's see. Oh, Kyle. Dude, excellent. Totally solid. At this point, even if all the stuff is in there, totally solid strategy. Even if all the stuff is there as published, I'm still going to bump it back probably to Wednesday just to, yes, totally. Actually, let me just go into assignments and modify the due dates. I'm going to bump it definitely to Wednesday, even if all the stuff is good to go. Yes, Amanda, I totally can. I totally can. Here, hang on one sec. Okay. Let me pull up exercise 4. Okay, yeah. Here, let me So basically the way there's kind of 2 parts to exercise 4. One is assigning oxidation states inside molecules, and then the second is basically here's a redox reaction. Assign all the oxidation states. Determine the substance that's oxidized, the substance that's reduced, which are, we're talking about the individual elements, and then determine the reducing agent, oxidizing agent. Okay, Maya, let's see, for eLab 4, do I use experimental data from the video to fill out the worksheet, or do I need to go on the Beyond Labs? Okay, and then experiment 5, worksheet submission, I did not see. Jason, so quick question. Hang on one sec. second. Okay. Jason, so I haven't posted the Experiment 5 stuff. I'm a little behind getting that out. It'll go up at the very latest by tomorrow, and the due date will be later than the one that's in the the lab syllabus. Ludwig, I totally can. There's a couple questions ahead of you in the queue. So first I'm gonna do answer Amanda's question, which is a question about exercise 4. Then I'm gonna get to Maya's question, and then I'll hit yours up talking about the difference between work and heat. Okay, but first, sorry, let me just pull up trying to go to the redox problem. Let's see here. There we go. Here we go. 240. Okay. Really, the Experiment 5 worksheet tab is on Canvas. Let me just look at our assignments. Oh! Yeah, here. Sorry, Jason. I see that. Here, I temporarily took it down. When it reemerges, it'll have the proper submission date. But I just altered that on Canvas. Okay, Eric, let's see. Push back, something not posted for the lab. Eric, I'm going to answer your question really quick. To be totally honest, Eric, I'm not exactly sure if there's something not posted. I feel like it's fine. I haven't heard anything from the other professors, but so we're all taking turns putting together the e-labs, and I didn't do this one specifically, so I'm not exactly sure. Yeah, totally. So I'm gonna. So I don't know if it's missing something. I'm gonna check it out. But in any case, I'm gonna clear it up for our class tonight. I think it's okay, but I just bumped it a couple days just in case it's not, because I think there's some students who haven't been able to start working on it for whatever reason. So that's why I pushed it back, just to be safe. But I think if you've already finished it, I think you're good. I think some people might be missing something, but I don't know what. So I'm gonna look into it. Okay, let's take a look at. Okay, so Amanda, thank you for being patient. Here is a problem that is similar to the ones you encounter on exercise 4. All right. Where did that problem go? Okay, here we go. So we've got, this is the synthesis of Aqua Regia. So we have a reaction where 3 moles of sulfuric acid react with 2 moles of nitric acid to produce 2 moles of NO gas plus 1 mole of water. Oh, sorry, this is not sulfuric acid. This is sulfurous acid. Sulfuric acid is one of the products. So we're going to do, whoops, didn't mean to erase that. We're going to do 3 things with this. We're going to, part A, assign all oxidation states. B, we are going to determine the substances, I should say, that are reduced and oxidized. And then C, we're going to determine the oxidizing and reducing agents. All right. So first off, let's work on assigning our oxidation states. Let's start with sulfurous acid. So whenever you have... Kate, great question. And the answer is they do not. Because what determines the oxidation state is the chemical formula. And so if you just have the chemical formula of every reactant and every product, you can assign all the oxidation states without balancing. Great question. All right, so with the rules of assigning oxidation states, hydrogen is +1 whenever it's with other nonmetals, and sulfur and oxygen are nonmetals. Between sulfur and oxygen, we got to jump to rule number 4. The more electronegative is going to take its regular ionic charge. Oxygen's more electronegative than sulfur, so it'll be a -2. Now we have to actually determine sulfurs, because we know that 2, oops, should want that in black, 2 times the oxidation state of hydrogen plus the oxidation state of sulfur plus 3 times the oxidation state of oxygen equals our total charge in sulfuric acid, which is 0. All right, so we've got 2 times positive 1 plus sulfur plus 3 times oxygen's oxidation state, negative 2, is equal to 0. So we have positive 2 plus sulfur minus 6 equals 0. So if we have sulfur minus 4 being equal to 0, then that means that sulfur has an didn't mean to bump that. Sulfur has an oxidation state of plus 4. All right, let's move to nitric acid. Hydrogen's plus 1. Oxygen's more electronegative than nitrogen, so it'll have an oxidation state equal to its regular ionic charge, negative 2. So this, now we can solve for nitrogen's oxidation state, because the oxidation state for hydrogen plus the oxidation state for nitrogen plus 3 times the oxidation state of oxygen is equal to our total charge, which is 0. Hydrogen is plus 1. Nitrogen is unknown at this moment. And oxygen's is negative 2. So we have 1 plus nitrogen minus 6 equals 0. So nitrogen, the oxidation state of nitrogen minus 5 is equal to 0, which means that nitrogen's oxidation state is plus 5. Plus 5. There we go. Now looking at the product side, for NO, oxygen's more electronegative. That'll be negative 2. And since nitrogen plus oxygen has to equal our total charge, which is 0, nitrogen in this compound is a positive 2. For H2O, hydrogen's oxidation state will be plus 1 because it's with a nonmetal. Since we have 2 positive ones, oxygen must be negative 2 to balance. All right, finally, we're at sulfuric acid. Hydrogen's a plus 1 for reasons already discussed. Same with oxygen. All right, now we have to find sulfur's oxidation state. 2 times the oxidation state of hydrogen plus the oxidation state of sulfur plus 4 times the oxidation state of oxygen is equal to our total charge, which is 0. So we've got 2 times a positive 1 plus sulfur plus 4 times negative 2 equals 0. So we've got positive 2 plus sulfur minus 8 equals 0. So sulfur minus 6 equals 0. So sulfur has an oxidation state of positive 6 in sulfuric acid. All right, so we have done part A. If you look back at our, not our any questions. Look back at, where is it? It's up here. We have assigned all the oxidation states. Now we need to determine, Kate, great question. Because we know when you're determining oxidation states, whoever is, so nitrogen versus chlorine. So if you look at them, nitrogen is 1 space higher, but chlorine is 2 spaces further to the right. So chlorine, in chlorine versus nitrogen, chlorine is more electronegative because it's 2 spaces further to the right. All right, but let's make this comparison a little harder. Let's compare oxygen versus chlorine. All right, oxygen is one higher. Chlorine is one further to the right. Which one wins out? In this instance, when it's one versus one higher versus one further to the right, the one that is higher will break the tie. But in the case of chlorine versus nitrogen, chlorine is because it's 2 spaces further to the right as opposed to nitrogen's 1 space higher. So that's nitrogen versus chlorine. And then second question, when determining how many electrons are exchanged in a redox reaction, do you pay attention to the stoichiometric coefficients? So that is a great question. Yes, Kate, you're totally welcome. When you're determining when you're determining how many electrons are exchanged, it's determined by the number of electrons you need to balance your charges. So you remember when you're using the half reaction method, you first balance your atoms, then you balance your charges, and to balance your charges can only add electrons. And so the number of electrons you need to add to balance the charges of your half reactions, that'll determine how many electrons are exchanged in the redox reaction, if that makes sense. All right. So now that we've assigned our oxidation states, again, just a quick reminder. Now that we've assigned oxidation states, we need to determine the substances that are reduced and oxidized. And to do that, we need to identify what oxidation states are changing. Kate, I can do an example in just a second to kind of refresh your memory. But I'll finish working this problem first, and then I'll show you in the I'll show you visually, because a picture's worth 1,000 words. So to find out who's oxidized and who's reduced, you need to look for changing oxidation states. One that changes, sulfur starts at +4 and ends at +6. So sulfur's oxidation state changes. It is going to be one of the substances that is either oxidized or reduced. The other oxidation state that changes is nitrogen. Starts at +5, ends at +2. So nitrogen is changed as well. If we look at sulfur, sulfur goes from a +4 to a +6, which means that it loses electrons. That means sulfur is the substance that is oxidized. So sulfur is oxidized. When you look at nitrogen, nitrogen goes from a +5 to a +2, so it's getting less positive, which means that it gains electrons. So nitrogen is the substance that is reduced. All right, so now we've determined the substance that is oxidized and the substance that is reduced. It's sulfur's oxidized, nitrogen's reduced. Now we need to determine the agents, all right? And so you look, for example, at the compound containing sulfuric acid, and the compound containing sulfur, and you ask, what causes the oxidation? And the answer is nitric acid, HNO3, is the reactant that causes the oxidation to happen. It's what reacts with sulfur. So we say that HNO3, nitric acid, is the oxidizing agent. And we're going to look at nitric acid, because nitrogen is reduced, and ask the same question. What reactant reacts, causing that reduction in nitrogen? And the answer is sulfuric acid. So sulfuric acid sorry, not sulfuric, sulfurous acid is the reducing agent. All right, and that is how you solve. That is how you solve. Basically, all the problems on exercise 4. These are the harder ones that are at the end, where you've got to find the oxidizing, reducing agents, the substance that's oxidized, substance that's reduced, and then assign all the oxidation states. The ones before just give you a molecule and ask, what's the oxidation state for hydrogen in this, or chlorine, or whatever. So Amanda, that is the answer to your question. Kate, really quick. Kate, great question. Oh, Amanda, you are so totally welcome, dude. Thank you for asking such a great question. Let's see. All right, so real quick, before I bounce to the next question, since we're kind of talking about oxidation reduction, and Kate, you had a question about how do you know how many electrons are exchanged in a redox reaction. Here's how you know. So, for example, here's how you determine the, okay, so here I'm going to write an example. Oh, you know what? Okay, yeah, I'm going to do this example. So determine the number of electrons exchanged in the following redox reaction, which is the reaction between aluminum metal and chlorine to produce aluminum cation and chloride anion. All right, so the way you're going to answer this question is you're going to balance this using the half reaction method. So we're going to isolate aluminum and chlorine, and we're going to balance these two reactions. So first, we're going to start with aluminum. You've got to balance the atoms, and we're already balanced, right? There's one aluminum ion in, one aluminum atom on either side. Next, we have to balance our charges, and on our reactant side, there's no charge. On the product side, there's 3 charges, all right? And we need to make sure that the charges are the same on both sides of the reaction. And we can only do that by adding electrons. So you can only add negatives. And so we need to add negatives to the product side to bring it down to 0. So we're going to add 3 electrons so that we've got a to balance our charge of positive 3. We've got a positive 3 minus 3 negatives. Now our charges are balanced for our aluminum half reaction. All right. Now, all right, let's look at the chlorine half reaction. So first, the first thing we got to do is we need to balance our atoms. To do that, we need to multiply chloride by 2. That way we have 2 chlorines on our reactant side and 2 on our product side. All right. Now we need to balance our charges. Again, we've got 0 charge on our reactant side and then 2 negatives on the product side. Now, to balance here, again, you can only use electrons, so we can only add negatives. If we add negatives to the product side here, it's only going to get more negative further away from 0. So to balance this, we need to add 2 electrons to our reactant side. And now we have -2 plus 0, which is equal to -2. And now our charges are balanced for both half reactions. All right. Now, to balance a redox reaction, you got to balance your atoms and charges for both half reactions, but then you have to balance your electrons. You got to make sure that the number of electrons being produced by the oxidation half reaction are equal to the number of electrons being consumed by the reduction half reaction. You can see here that 3 and 2 don't go into each other evenly. So to balance the electrons for this redox reaction, we need to multiply our chlorine half reaction by 3 and our aluminum half reaction by 2. So the aluminum half reaction becomes 2 atoms of aluminum. Okay, yes, totally. I knew like once I wrote it out, it would make more sense. Because again, a picture is worth 1,000 words. So that's the aluminum half reaction. The chlorine half reaction, we've got 6 electrons on the reactant side, plus 3 molecules of Cl2 producing 6 chloride ions. All right, now, if this were a balance or redox reaction problem, this is where we add them together and we get 2 aluminum react with 3 molecules of chlorine to produce 2 aluminum cations and 6 chloride anions. And that's the balanced redox reaction. But to answer our question, to determine the number of electrons exchanged in this reaction, the answer is 6 electrons are exchanged. Because the number of electrons that get exchanged is equal to the electrons, the balanced number of electrons for your redox reaction. So that is how you handle that part. Okay. So that first question and then the questions it generated carried us 30 minutes into office hours. Let's see. Okay. Maya, you've been waiting patiently. Lab 4 to use experimental. Okay. Let me check this situation out. Let's see. All right, so this is the reactivity series. let's see. The main eLab page says get our worksheet data from Beyond Labs, but the worksheet says use the video. Okay, totally. So let me get to the bottom of this. Boom. Ah, yes. Okay, I am so sorry. That is confusing. I totally see it now. Where it says do the video and then collect them from Beyond Labs. Okay. So my totally use the data from the video. I apologize for the confusion. I am going to I'm gonna post an announcement. Okay, edit. Oh, dude, yes. Thank you for bringing it to my attention, too, because, yeah, the lab page said use Beyond Labs, but then the pre-lab said use the video. And so I apologize for the confusion. Oh, wait, I edited the due dates in the actual due dates, but I'm just updating it in the page. So we'll bump this due date to Wednesday. If you haven't... Yeah, oh, dude, it's totally not your bad. Different instructions were posted for this thing, so all right. So I'm just gonna write a note for the rest of the class. Let's see. Okay. All right, let's see. Scrolling back up. Okay, Maya, we got, thank you for that question. Jason, we did that. Okay, Ludwig, you have been patiently waiting. I so appreciate um, your patients. Let's talk about. Let's see, where is it? The concept of work in comparison to heat. All right. So, oops. So here's really the way to think about it. All right. So here's the way to think about this. So work and heat are two different pathways through which energy is transferred. All right, there are two different pathways through which energy can be transferred. That's really the way to think about it. There are two different roads, two different ways that you can transfer energy from one thing to another, from system to surroundings, from surroundings to systems. All right, now heat, the way heat transfers energy, heat transfers energy when there is a difference in temperature. So when there's a difference in temperature between two things that come into contact, energy is going to flow from the thing that's hot into the thing that is cold. All right? There's a difference in temperature. There's going to be a thermal energy transfer. Now, work transfers energy when there is a difference in pressure. All right. Just like with heat, when there's something hot, something cold, the hot thing's going to transfer energy to the cold thing. When there's when you've got two things that are separated from each other that are under different pressures, the high pressure system or surrounding, the high pressure entity is going to transfer energy to the low pressure energy by compressing it. All right. So you've got these two things that are separated. One's high pressure, one's low pressure. The high pressure thing is going to push its way in on the low pressure thing, compressing it, transferring energy, just like when you have a high temperature and a low temperature system, entities that are in contact. The high temperature entity transfers energy to the low temperature energy. So really, it's whichever one that's at the higher energy state, whether it's a thermal temperature or a work-based pressure, will transfer energy to the lower energy state entity, because that's just the way things flow. They're always moving towards equilibrium. The high pressure system will crush the low pressure system until their pressures are equal. The high temperature system will heat up the low temperature system until those two temperatures are equal. So that's, I guess, kind of a different conceptual way than what I approached, the way I approached explaining it in class, but that's the difference between energy and work. Often we think energy has to do with temperature, and that's because we have more of a intuitive grasp of what thermal energy is. Work energy is energy that's rooted in the pressure of a system versus the pressure of the surroundings. How does work relate to Dalton's law? That's a good question. When you look at Dalton's law, simply states that if you have a mixture of gases, so like that your total pressure is going to be equal to the individual pressure of each gas that's a component of that mixture. So Dalton's law and work aren't explicitly related, because you only have work being transferred when you're experiencing a change in volume. When your volume is increasing or decreasing, when you're expanding or being compressed, that's when work, that's when energy is being transferred through work. So it doesn't really connect with Dalton's law all that much, because Dalton's law just says that the total pressure of a mixture of gases is equal to the individual pressures all added up. Okay, Kate, sorry, that yes was to the second thing. Is that why change in enthalpy is Q at constant pressure? Let's see. Also, I'm looking at your first question now. For the oxidation state of C2H5OH, yes, actually, yes, twice over. So when you're calculating the oxidation state of carbon, you've got the -2 for oxygen, the +6 for hydrogen. So you've got 2 carbons plus 4 equals 0. Subtract 4. So 2 carbons equals -4. Divide both sides by 2. So carbon comes out to be an oxidation state of -2. Amanda, you are so welcome. Kate, fire away. And I will start firing up my textbook. Chapter 5, number 78. Dude, Chapter 5 has been a a popular chapter for these homework problems. What's been really fun for me too is actually, so I've been teaching out of this edition of the Cho textbook for several years now. I think I started teaching out of it in like 2016. So that's when, like, I went, when I first teach a class, that's when I go through and I pick out all the homework problems. And you don't always get asked every homework problem every year. And so, like to be totally honest, Kate, the questions that you asked last time that I made the announcement, like, dude, check these out. We worked some really good problems. I hadn't actually done them for years. And so with the ones that get asked year after year, I kind of remember how to do them. These ones I hadn't, and I was like, dang, these are some challenging questions. Like, these are some really good questions. It was fun to work them because I got to see them with new eyes, so to speak. All right. Okay, so let's see. Okay, so we got 1 from chapter 5, and then 3 from chapter 6. Let's take a look at this. So this is, whoops. Yeah, it was a fun excursion for me. As well. Okay, so let's check out 78. So, ozone is depleted in the stratosphere by chlorine from CF3Cl, according to... Oh, excuse me, sorry about that. According to this set of equations, and they give us 4 different reactions. What is the total volume of ozone produced at a pressure of 25.0 millimeters of mercury and a temperature of 225 Kelvin? Let's see, wait, what is the total volume of ozone? Ozone at a pressure, okay, and temperature, that is destroyed when all the chlorine from 15 grams of CFCl3 goes through 10 cycles of the given reaction. Or reactions. Okay, excuse me. All right. Okay, so here's the point of this. Okay. Here. Let's start with. So this is the reaction that destroys the ozone layer. Which fun story. The chemists who figured this out and then won a Nobel Prize for it later. Or faculty at my alma mater, UC Irvine. All right, so here's the reactions. There's 4 of these. Yeah. He was professor emeritus when I was there, which means that you're kind of like faculty forever, but you're like not research active. You're kind of low key retired, but you're still super important because of what you did, and all that good stuff. So I didn't actually get to take any classes from him, but I saw him one time. At a symposium. All right. So, this is the set of 4 reactions that destroys ozone, and they want to know what the volume of ozone at this given pressure and temperature, what volume is destroyed when all the chlorine from 15 grams of CFCl3 goes through 10 cycles of this given reaction. Now here's the deal. You may be wondering what's with these 10 cycles. You'll notice that the first reaction that destroys ozone happens right here. And it's when a chlorine atom, you'll notice that's not Cl2, that's just Cl as an atom, it's a free radical, reacts with ozone, destroys 1 molecule of ozone. But you'll notice that hypochlorite and oxygen come together in a second reaction to create another chlorine atom, which can then go back to this reaction once it's regenerated and destroy another molecule of ozone. So this is why Freon, which is the CFCl3 is a type of Freon. It used to be used in cooling. It's not used, they're not used anymore because this reaction repeats itself because chlorine actually regenerates, it's catalytic. So it never goes away and it'll just destroy, it just eats up ozone molecule after ozone molecule after ozone molecule and never stops. So in a normal problem, they'd say how much would be consumed, how much ozone would get destroyed if 15 grams of this stuff reacted. But here's the thing is 15 grams of this stuff, once it makes chlorine, will never stop reacting. So we're going to do the normal problem, calculate how much gets destroyed by 15 grams, but then they want to know how much gets destroyed when 15 grams goes through the cycle 10 times. We're just going to multiply our answer when we find out how much 15 grams will destroy. That's 1 cycle. We just multiply that by 10. So that's the only real twist in this problem. All right. So first, let's figure out. Okay, and I guess just one thing before I dive in, I should set this up properly. So they want to know they are asking us to find the volume of ozone, and they give us the pressure of ozone, 25.0 millimeters of mercury. They give us the temperature, which is 225 Kelvin, and they ask for volume. If we're going to solve this, we want to find volume. We're given pressure and temperature. We always know R. We need to find the moles of ozone. To do that, we're going to do some stoichiometry. Then we're going to use the ideal gas law to find our volume. And that'll be for 1 cycle. We'll multiply by 10. So that's kind of the strategy. That's where we're going. Now let's do our stoichiometry. We've got 15 grams of CF3Cl. Step number 1, we need to convert from grams of CF3Cl to moles. All right, and just doing this calculation real quick, carbon, molecular 12.01, fluorine 19.00, and chlorine 35.45. We gotta multiply fluorine by 3. So 19 times 3 plus 12.01 plus 35.45. So that adds up to be excuse me, sorry for sneezing. It is allergy season for me. I don't really get allergies in the spring, but for whatever reason, autumn just kills me, so that's why I'm a little sniffly. All right, so we have canceled grams of CFCl3. Now, oh, thank you. Now, we need to find the moles of ozone, and you'll notice that we don't know. But we do know that 1 mole of CFCl3 will produce 1 mole of chlorine atoms, so we can convert totally. Yeah, it's just people think spring, which makes sense, right? Things are blooming and stuff, but I don't know, whatever it is that sets me off always happens in the fall. Our first reaction allows us to convert from moles of CFCl3 to moles of chlorine, and that is a 1-to-1 mole ratio. Now, the second reaction allows us to convert from moles of chlorine to moles of ozone. Oh, here, hang on one second. Sorry, I apologize for my sniffling. Okay. Hang on, actually. I jumped in here prematurely. Let me dial this back. I'll show you why. So sorry, this is 1 mole CF3Cl. Okay, I'm gonna zero this out for a minute. They want to know how much ozone is destroyed in an entire, or in 10 entire cycles. To figure that out, we actually need to add all these things together. All right. So you'll notice some things cancel. Like one of these chlorines. Whoops. Nope. One of these chlorines cancels with this one. Hypochlorite cancels with this hypochlorite. And this oxygen atom cancels with this oxygen atom. When you add everything together, you'll notice that you have CF3Cl plus, you'll notice that there are 2 ozones on your reactant side, so this is going to be plus 2 molecules of ozone, O3, plus UV light. Produce, and then on our product side we have CF3, we have a Cl, and you'll notice we have 1, 2, 3 moles of O2. So this is the mistake that I almost made. And that is this. Let me bump this down. Whoa, not that down. Let's bump this down. Okay, hang on. I apologize if this is looking confusing. There we go. So you'll notice that the ratio from CF3Cl is actually 2 moles of ozone is actually a 1 to 2 mole ratio. So 1 mole of CF3Cl produces 2 moles of ozone. And this is where we can stop here because we just want to know how many moles of ozone are there, and then we can use the ideal gas law. All right, so let's crunch our numbers. We've got 15 divided by 104.46 times 2. This comes out to 287 moles of O3 get destroyed. All right, now, at long last, we can calculate. No, not that one. Wait. Now we can calculate with the ideal gas law. Well, almost. First, we need to convert our pressure from millimeters of mercury to atmospheres. Okay. So that's 760. So 1 atmosphere. And so let's see. 25 divided by 760 is 0.0329 ATM. We need to convert. Oh no, we don't need to convert our temperature. Right, temperature is 225 Kelvin, and then our moles 0.287. All right, so if we look at PV equals nRT, we can find our volume if we divide both sides by our pressure. So volume is equal to 0.287 moles. Our 0.08206 liter atmospheres per mole Kelvin. 225 K. And then we have our atmospheres, 0.0329 ATM. Moles cancel, Kelvin cancels, and we're left the volume in liters. So let's crunch our numbers. 0.287 times 0.08206 times 225 divided by 0.0329. So whoa, what just happened? Sorry, my brush size got bumped to 2500 pixels. Let's drop that down to 27. Volume is 161.064574 liters of ozone are destroyed in one cycle. All right, but in 10 cycles, 10 cycles will be 1,610 liters, right? Because that is that multiplied by 10 with the proper number of sig figs, because we should be landing with 3. All right, so that is the answer to number 78. Pretty intense. Again, this one is actually another example that's something this gnarly would be a little bit above exam caliber, like harder than what I'd put on a test. But if you can grapple with something on this level, you'll be ready for what I put on a test. All right, the next few questions you have are coming from Chapter 6. So let me navigate in that direction. Oh, okay, right. Kate, great question. I mean, the correct way to do things is always wait to round to the end. Honestly, in an exam context, I would be, so this is my pro advice. It doesn't really matter in a multiple choice setting. If I give you a multiple choice where there's several answers to choose from, it doesn't really matter, because even if the answer you calculate is 0.292 and the available answer is 0.293 as opposed to out of several others, there's only going to be one that's close to your calculated one. So if you're doing a multiple choice problem, don't stress. If you're doing a numerical entry problem where you're going to enter the actual value, be super picky, because in that instance, it can make a difference. So I would be lax for multiple choice, and then I would be rigid for numerical entry problems. Okay. Okay, so we're moving on to chapter 6 here. Number 40, part B. Kate, you are so totally welcome. The funny thing is, when I was doing that problem and there was that part with the atmospheres where I rounded to 3, even though, you know, I always say like, oh, always wait till the end. I did it because I did it kind of without thinking. And after I did, I was like, I bet she's going to ask me about this. Because I was like, you're just sharp, and I had a feeling that you'd catch it, and then you did. So That was funny. Okay. Let's see. So number 40, chapter 6. Oh wait, hang on. I apologize. I accidentally unplugged my laptop. Totally. Yeah. So Kate, that would be a great way, for example, to save some time. On the test, when you're dealing with multiple choice, it's not going to be as big of a deal if your answer's a few decimal places off. But for a numerical entry, it's got to be exactly correct with the correct sig fig. So that's when I would take my time. But for the other ones, I'd speed through them. And that's how you play the game. All right. Let's see. Okay, so finally, number 40. Identify each energy exchange as primarily heat or work and determine whether the sign of the change in energy is positive or negative for the system. Huh. Okay. A book is dropped to the floor. Okay. Sorry. I laughed because part C says a father pushes his daughter on a swing. I only saw it I was just glancing and I just saw the corner of my eye. A father pushes his daughter. I was like, wait, what? What kind of problem is this? Well, so here's the deal. Okay. So when you're doing a problem like this one, so work is for us, right? Expansion or compression of gases. So if you are this is so we don't have a gas being expanded or compressed here. So I would roll with thermal. Reality is a book that's dropped on the floor. This is a situation where potential energy is being converted to kinetic energy. And then converted back. So I would lean thermal for this one. Reality is though, just so you know, I wouldn't include a question like this on the test. I'm gonna stick to more computational and I wouldn't go kind of conceptual abstract like this. Okay, Ludwig, let me see. Off topic, but you're having trouble understanding what the purpose of doing time tests and cranking out many problems on the exam. Ludwig, great question. And here's the deal. The reason, well, so yeah, I mean, so here's the reason is in this kind of online world, online education world that we live in, here so here's really the challenge is I mean, just in general, this actually is not just online, but all exams are there to see what you know. And all exams are there to see what you know within a time constraint. So even if we were meeting in person, the exams are still going to be timed. And the feedback that I get from my students when we meet in person, like before COVID, is that time is an issue on those as well. So you don't want to make the mistake of thinking that time pressure is only an issue because you're taking an online class from me. If you were taking a class from me where we were meeting, you'd be facing the same situation. When I give an exam, there are some people who finish early. Most students have to take the entire time to take the tests because that's the type of test that I rate. Now, so that's just in general. Time pressure is always been a part of every exam that I've given for like 90 to 95% of the class. On top of that, in this online educational world that we find ourselves living in, the time is the only entity, the only quantity that's there to ensure, what am I trying to say? The time constraint's there because in a time pressured situation, it forces you to take what you know and apply it as quickly as possible. And if you had to take the same test with unlimited time, you'd probably be able to Google your way to get to most of the answers. Not necessarily a numerical value, right? Like, because I write my own problems, I don't pull them for anywhere else. So it's not like you take this problem, Google it, and get the numerical value and punch it in. But you would, given an unlimited time, be able to Google, be able to look stuff up, be able to figure out how to do problems because the internet's telling you how to do them, which would defeat the purpose of the exam. The point of the exam is, what do you, the individual, know? What can you, the individual, do? And so that's why the tests are timed, because I'm not interested in your ability to Google. That's a different class. I'm interested in what is your comprehension of the chemistry concepts and topics we've been discussing. And the only way to ensure that it's actually coming out of your head and not coming from somewhere else in the internet is if there's a time limit. Now, that being said, the way that I determine how long to give the class is, so I sit down, I write the test, right? I look at how, what topics need to be tested on, what we got to cover. I figure out how many of each. I write it out. And then when it's done, I take it. Yeah, thank you. I take the test myself. And I time myself. And I'm not like cranking through. I'm not like working it as fast as I possibly can. But I'm doing every algebraic step. I'm entering the numbers in my calculator. I'm crunching the numbers just like I do it. And I'm timing myself. And however long it takes me to take the test, I give the class double that time. And I'm not like flexing like, oh, it only takes me half. That's not what I'm doing. The reason why I measure myself taking the test is because I'm measuring how much time does it take to physically write out every step. And then when I double it, that tells that the reason why I double it is it takes so much time to physically write out and punch all the numbers into the calculators. That means that half the time on the test you're going to spend physically writing or, working the problems. The other half of that time is there for you to think. So half the time is for manually doing the problem. Half of the time is reading it, understanding it, figuring out how to solve the problem. So that's how I arrive at the time for the class. The class gets double the time it takes me to complete the test. Which, as you know, is a time pressure situation. So, which is why totally recommend when you start the test, it presents the problems in random order. I totally recommend going through it, finding the problems that are easy and quick and knocking those out first. Get the easy points, the for sure points early while your mind is fresh. And then after you've gotten all the easy points, go back and start doing the harder problems one at a time. That is the best method for success for taking any exam, not just my own. Because time is a pressure and time is a factor, you should take it into account in the strategy you use for taking the test as well. So anyways, I realized part of that last part wasn't part of your original question, but that's kind of the explanation for why time has to be a factor. One, it always is a factor. Two, I've got to test for what you know, not for what you can Google. But then three, because time is a factor, play that game and play it to your advantage. Do the fast ones easy and early, get as many points as you can that way, and then you'll have more time for the harder, more challenging problems that require more thought. Ludwig, interesting question. The answer is depends. Honestly, the answer is depends. In a real world context, it depends upon what you're doing in the real world. If you're doing engineering, the calculations are just as important, if not more so, because if they're off or they're sloppy, it can have disastrous results. So it's a mix of both. But the other thing is, for the problems in this class, to be able to do the calculations, you also need to understand the concepts behind the problems to be able to solve them. So there's really, in chemistry at least, no divorcing one from the other. They're kind of inextricably connected, so to speak. But it's a very interesting question you raise. Alrighty. So let's take a look at chapter 6. Oops, that in black. Chapter 6, number 57, was it? 67, sorry. Oh, Leanna, let's see. So Leanna, great question. The answer is I'm not sure, actually. I don't know. Professor Mahoney gets the final say over the type of exam, format of exams, for his lecture. I have control over mine. This is his, first day back from paternity leave. He's also our department chair, so he has a lot of responsibility on his plate, and so we haven't talked about yet whether or not we're going to collaborate on exams, if they're still going to be the same, or if I'm just going to write mine and he's just going to write his. So I don't know. There's a possibility that we might choose to make them the same and kind of help each other out, or we might kind of function independently. So I don't know what the plan is at the moment. But he is the person who gets final say in your section. So I would maybe direct that question at him and see what he's thinking. We haven't talked about it. He may just want to write his own tests. And to some, that's almost what I would expect, because every professor kind of emphasizes different things. I mean, the basic content is always the same, but I might spend more time on something that he spends a little time on. He might really dig into something that I like mentioned but don't emphasize. So my guess is they would be different. I don't know what his testing style is because I've never taken Gen Chem from him, so I don't know if time constraints are going to be similar, softer, harder, etc. So all those questions would be to get the most accurate answer, direct him towards him. And of course, you're totally welcome to pop by office hours, ask questions, show up. You can show up to my lectures, ask questions there. It's totally open doors. If I offer any resources that you find helpful, you're more than welcome to use them and participate. All right. Okay, so let's take a look at chapter 6, number 67. Let's see. Okay, so I'm just going to go ahead and write this problem out. Oh, wait. Oh, sweet, I did that right. Okay, so let's take a look. So 31.1 grams of a 31.1 gram wafer of pure gold. Just gonna put AU. At 69.3 degrees Celsius. Oh, dude. Leanna, you're rad. I was gonna say so I know like half the students are from one section, half are from the other. But when you asked just now, I was like, oh, she's in the other one, because you have made both lecture and office hours so much better than they would have otherwise. You always bring great questions, and so there's like this little part of me that was like sad, like, oh no, I'm losing her. But if you still show up, then I've got no reason to be sad. So thank you for all the great participation, and I'm glad that that it's not over. We can party all semester long. All right, so we've got 31.1 grams of gold at 69.3 degrees Celsius, submerged into 64.2 grams of water at, oh, this is a great problem, 27.8 degrees Celsius in an insulated container. All right, this is a great question. What is the final temperature for both substances? And something we should be aware of. So I already mentioned this in lecture, but these problems do not include specific heat capacities. So we have to look these up. The specific heat capacity of water is 4.184 joules per gram degrees Celsius. But we need to know what the specific heat capacity is of gold. And wow, it's not very big. Specific heat capacity of gold is oh wait, hang on. Yeah, is 0.129 joules per gram degrees C. All right. Yeah, or 0.128. Totally. Here, well, we can use that value. All right, now. Oh, wait, let me open this in a new slide. All right. So what are we trying to find? We're trying to find our final temperature, which is, we know the final temperature for water is equal to the final temperature for gold, because that's the thing about these calorimetry problems is the thing that's hot and the thing that's cold reach thermal equilibrium, so they're going to be equal at the end of the day, the two final temperatures. What are we given? We are given a mass of gold, right? 31.1 grams. We're also given a mass of water, 64.2. We have the heat capacity of gold. Right, it's 0.128 joules per gram degree C. We have the heat capacity of water. And we have two initial temperatures. Initial temperature for gold is 69.3 degrees Celsius. We have an initial temperature for water, 27.8 degrees Celsius. All right. Now, I've mentioned before that an important aspect of solving these types of problems is writing out the equations for the quantities that we're being asked to find. And we have two sets of equations that have our final temperature in them, right? We've got our delta T for gold, T1 of gold, minus T2 for gold, and we have our delta T for water. Sorry, I flipped these around. It's final minus initial. All right, now when you look at these equations, we know our initials, but we don't know final. That's what we're trying to find, and we don't have enough information yet for delta T. I said yet, though, because we're not done looking at our equations. Right? We know that there's an equation that has... Oops, hang on. We have equations that have delta T in them. Right? We can write out Q for gold is mass of gold, specific heat capacity of gold, change in temperature of gold. We also have all this for water. It's equal to the mass of water, specific heat capacity of water. Whoops, I'm almost writing gold here. Now, if you look at these, we know mass and specific heat capacity for each of them. But again, it feels like we're at an impasse because we don't have the energy absorbed by water. We don't have the energy released by gold. And we're still at an impasse with the specific heat capacities. This is where the single most important equation for these problems comes into play. That is your system, Q for your system, is equal to -1 times Q for your surroundings. This is the golden equation for these problems. Watch what this allows you to do. All right, I'm going to go to a new slide. Oops. So I'm just going to rewrite what I had going on. Thermal energy transferred from the system is equal to -1 times the thermal energy absorbed by the surroundings. We know what thermal energy absorbed by gold is, right? It's the mass of gold times the specific heat capacity of gold times the change in temperature of gold. That's Q of gold, right? This is equal to -1 times thermal energy gained by water, mass of water, specific heat capacity of water, change in temperature of water, right? Now, at this moment, we know mass of water, specific heat capacity of water, and the mass of gold, specific heat capacity of gold. But we don't know these yet. But these two have equations. Let's substitute in. Mass of water times the specific heat capacity of water times final minus initial. This is equal to -1 times the mass of water times the specific heat capacity of water times final temp minus initial temp. All right. Check this out. At this moment in time, we know mass, specific heat for both of these. We also know initial temperature of gold. We know initial temperature of water. So as of right now, we have one equation and only one unknown. So all we have to do is solve for our final temperature, and this is going to take a buttload of algebra. But I'm willing to do it. I shouldn't ask you to do it if I'm not willing to do it myself. So we're going to start by distributing what's outside of parentheses to the inside. All right? So we've got the mass of gold times the specific heat capacity of gold times T2 minus the mass of gold times the specific heat capacity of gold times the initial temperature of gold, which is different than water, is equal to, just wait, this will take a long time. It's not horrible, it's just lengthy. This is equal to the mass of water times the specific heat capacity of water times the final temperature. Plus, so that's a minus, because minus 1 times a positive, now minus 1 times a negative is a positive, plus the mass of water times the specific heat capacity of water times the initial temperature. All right, now remember the goal. We need to isolate T2. I am so sorry. I couldn't contain that sneeze. We need to isolate T2 on one side of our equation, right? So let's start by adding this quantity to both sides of our equation. All right, we're going to add it over here as well. All right, but we need to isolate it. So we also need to get rid of this quantity, this mass of gold times specific heat capacity of gold times T1 of gold. So we're going to add this to both sides of our equation as well. Thank you, Stephanie. I appreciate that. All right, after we add all these things together, so these two cancel, and these two cancel, so we get the mass of gold times the specific heat capacity of gold times T2 plus the mass of water times the specific heat capacity of water times T2. This is equal to the mass of water times the specific heat capacity of water times our initial temperature of water plus the mass of gold, specific heat capacity of gold times the initial temperature of gold. Now, we need to solve for T2. So we need to factor it out of the left side of our equation, which I'm going to do on our next slide. All right, so we will have T2 times the mass of gold times the specific heat capacity of gold plus the mass of water times the specific heat capacity of water. And this is all equal to the right side of the equation, has not changed, which is the mass of water times the specific heat capacity of water times the initial temperature of water plus the mass of gold times the specific heat capacity of gold times the initial temperature of gold. All right, now we can isolate T2 on one side of our expression by dividing both sides by the mass of gold times the specific heat capacity of gold plus the mass of water times the specific heat capacity of water. cancels on our left side. So this is our final expression. T2 is equal to the mass of water, which is, let me find my original problem because I totally forgot what it was. Number 67. Our mass of water, which is, nope, 64.2 grams times the specific heat capacity, 4.184 joules per gram degrees Celsius, times the initial temperature of water, which was 27.8. Plus the mass of gold, 31.1 grams, times the specific heat capacity, 1.28 joules per gram degree C, times the initial temperature, which was 69.3 degrees Celsius, over the mass of gold, which is 31.1 grams, times specific heat capacity, 0.128 joules per gram degree C, plus the mass of water, 64.2 grams, times the specific heat capacity, 4.184 joules per gram degree Celsius. Let's take a look at our units here. On the top, grams cancel grams for both of those expressions. Oh, sorry, I was confused here. I wrote grams here, that should be degrees Celsius. Degree C cancel. And down here in the denominator, grams cancel. All right, let's do some number crunching. In the top, so T2 equals 64.2 times 4.184 times 27.8. That is 7467.4, and this is joules. I can only have 3 sig figs, so I'm going to put 3 spaces right there. Plus 31.1 times 1.128 times 69.3. So this will be plus 275.869 joules. I can only keep 3 sig figs here as well. Let's look at our denominator. Whoops. 31.1 times 0.128 is 3.9808, and heartbreaks. That's joules per degree Celsius. 3 sig figs there. Plus 64.2 times 4.184 is 268.61 3. Why not add one more? Joules per degrees Celsius. All right, let's add our... We're almost there. I can see the light at the end of the tunnel of this exceptionally long problem. Let's crunch our numerator. 7,467.4 plus 275.869. All right, so the numerator is 7,743.269. Our last sig fig in the numerator has got to be in the tens place. So we got 3 in our numerator. Units are joules. Let's add our denominators. 3.9808 and heartbreaks plus 268.613 is 272.5938. That's joules per degrees Celsius. This only has 3 sig figs too. So we got to roll with our less precise number. So the last sig fig in our answer is there, which means it has 3 significant figures. One thing you'll notice is that joules cancel joules, leaving us with degrees Celsius as our only unit. Let's do our last, punch our last numbers for this problem. 7,743.269 divided by 272.5938. The final temperature then is 28.405882 degrees Celsius, rounding to 3 sig figs. They'll have a temperature of 28.4 degrees C. All right, that is a massive problem. Well done to any and all of you who managed to hang in there throughout that thing. In the spirit of full disclosure, and this is the bonus material that you get access to when you hang out in office hours. A problem, so when I teach this class in person, I put a problem exactly like this one with this much algebra on every exam 3 that I write. Am I going to include one on this digital one? I haven't decided yet. It'll depend upon when I sit down, when I take it, if I think it's too much or too little. But there's a possibility that a problem of this challenge level could very well show up. So anyways, just be aware of that. Give this problem a crack. See if you can get there. Kate, you are so totally welcome. I think there's a couple more you asked for, right? Let's see, 67. Yeah, number 62 as well. Let's take a look. Chapter 6, problem 62. Let's see. Okay, titanium reacts with iodine to form titanium-3 iodide emitting heat. Excuse me. All right. Determine the masses of titanium and iodine that react. If 1.55 times 10 to the negative third kilojoules of heat is emitted by this reaction. Okay, so let's write this out. All right, so 62. So they give us a balanced chemical equation, which is nice. We have titanium metal reacting with iodine gas, producing titanium 3 iodide. And we're told that the delta H, change in enthalpy for this reaction, is negative 839. Now, the book says kilojoules, but delta H's are always measured in kilojoules per mole. So even if you run into a scenario that just gives it in kilojoules, it's always per mole. It's always some energy unit per mole. All right. So let's look at our sign. Delta H of this reaction is negative. That means it's exothermic. Which means that energy is produced by this reaction. It is released, and so we can write that 839 kilojoules on the product side of the reaction. Now, when you look at what we're given an energy, right? We're told that 1.55 times 10 to the third, I believe. Let me double check that. Yeah, 10 to the third kilojoules of energy were released, it was emitted by this reaction, and we're asked to determine the masses. We want to know how many grams of titanium and how many grams of iodine reacted to produce this energy. And just like any stoichiometry problem, we need a ratio to cancel energy and leave and get us to, for example, moles of titanium. And the ratio comes from the balanced chemical equation, because in the balanced chemical equation we see that 2 moles of titanium react to produce 839 kilojoules of energy. So we put 839 in our denominator, 2 in our numerator. Kilojoules cancel. Next, to find the mass of titanium that reacted, we need to convert from moles of titanium to grams. And this we pull out of our periodic table. 1 mole of titanium has a mass of 47.87 grams. Moles of titanium cancel. And now we have 1,500 times, excuse me, I apologize, times 2. 1,550 times 2. Divided by 839 times 47.87. Rounding to 3 sig figs. Gives us 177 grams of titanium reacted to produce this energy. To find the mass of iodine, we do the exact same calculation, but instead of titanium, we're going to do it for iodine, for I2. So we got to start by converting from energy units to moles of I2. And again, this ratio comes from the balanced chemical equation. 3 moles of I2 produce 839 kilojoules of energy. So kilojoules cancel. Next, we need to convert from moles of iodine to grams. Now, iodine is a huge atom. One atom of iodine has a mass of 126.9 grams per mole. And so 1 mole of I2 will have a mass of 253.8. Moles of iodine cancel. And now we crunch our numbers. 1550 times 3 divided by 839 times 253.8. Wow. So 3 sig figs, there we go. 1,410 grams of I2 must have reacted to produce to produce 1.55 times 10 to the third kilojoules of energy. And that is the tale of the tape. So I believe, at this moment in time, I've answered all the questions that have been at least asked so far, and I can totally answer any new questions. Just let me know. Ah. Rin, totally. Let me pull them up. All right, let's see. 8 and 9. Okay, so question 8. On the basis of the reactions you observed in the 6 test tubes, explain why the position of hydrogen can not be fixed exactly with respect to all the other elements listed in the activity series. Use experimental data and observations to explain your answer. Okay, so Rin, in the experiment, right? you're mixing a bunch of things together, and you're essentially trying to determine what is more reactive, right? So all the reactions are, you take some atom, react it with some ionic compound, AX, and theoretically the products will be A plus the ionic compound MX, all right? And the basic premise for this experiment is if a reaction occurs, then M, the element, is more reactive than A. All right. The element M is more reactive than the element A if a reaction occurs. All right. If no reaction occurs, it actually tells you something just as valuable. If no reaction occurs, then A is more reactive A is more reactive than M. All right. So that is that's the basic kind of premise for this lab, is you're comparing the reactivity between this element M and this element A. And if you observe a reaction, M was more reactive. If you don't, then that tells you that A, the thing that wasn't formed, is the more reactive of the two. And so in question 8, they want you to explain why you don't have enough information to say exactly so they want you to rank everything, like all the elements that you use in these reactions, or that were used in these reactions, and they want you to explain why you don't have enough information to say where hydrogen falls, if that makes sense. So that's question 8 in a nutshell. If I were to rephrase or rewrite question 8. Explain why you do not have enough info to rank H2's reactivity among the other elements tested. All right, so that's number 8. Let me take a look at number 9. What additional tests would be needed to determine the exact position of hydrogen in the activity series of elements? Okay, so the activity series, by the way, so this is a word that gets thrown around a lot. The activity series is simply this, ranking. Does that help? The activity series is just ranking the elements from most reactive to least. So with question 9, so question 8 is like, explain why there's not enough information to rank hydrogen. And question 9 simply says, basically, what reactions would you need to rank hydrogen? So that's the gist of what those two problems are asking. Anytime. Oh, let's see. Quantitatively, why is combustion... Oh! Kate, that is a great question. Kate, that is a great question. So, it actually has to do with... generically, when we're burning things, we're taking hydrocarbons. So for example, this is ethane. Oh, ethane's a gas. And we're making carbon dioxide and water. Here's the balanced chemical equation. All right, for the combustion of ethane, I think, does that work out? Wait, hang on. Yes, that works out. Okay, there's our balanced chemical equation. So, Kate, the answer to your question actually lies in the thermodynamics of bonding. So, breaking bonds absorb energy. Forming bonds releases energy. All right. So in every chemical reaction, you're breaking bonds, which is going to suck in energy, and then you're forming bonds, which is going to release energy. The question is, do the bonds you break absorb more energy than the bonds you release? And the stronger a bond is, the more energy it takes to break, but also the stronger a bond is, the more energy it takes or it releases when formed. And the key to the combustion is really right here. Water plays a role too. Water has some pretty good bonds, but carbon dioxide has one of the strongest bonds out there in nature is the carbon-oxygen double bond. All right, carbon-oxygen double bonds are very strong. And here's the thing. Carbon dioxide, the molecule, has two of them. Two carbon-oxygen double bonds. So a ton of energy gets released when CO2 is formed. And combustion reactions always form CO2 and water. You're basically taking three types of bonds that are weak-ish. The oxygen-oxygen bond, not that strong, and then the carbon-carbon and carbon-hydrogen bonds, they're not the strongest out there. You put in energy to break those, but then all the energy that gets released through the formation of water molecules, but especially the carbon dioxide, just releases way more energy than it took to break all the carbon-hydrogen and carbon-carbon bonds, or the oxygen-oxygen bonds in O2. So the answer to your question of why why is combustion an exothermic reaction, has to do with the stability of the products, the strength of bonds that you're forming that just release so much more energy than it costs to break the bonds of the reactants. All right, Ludwig, is the hydrogen bond stronger than CO2's bond? Um, Ludwig, great question. Um, it's definitely part of the answer. Um, there is more to it. Um, Oh, Ludwig, that is an interesting question. Um, so I really liked it in high school, which I know is not like the huge. Um, I mean, people's high school chemistry experiences can be very, very uh, different, and lots of it depends upon if your teacher's good or whatever. Um, and I just really really liked it. Um, I don't know why. I just thought it was insane that we could know this much about stuff that was so small and we couldn't see. Um, and like I enjoyed biology, but I didn't love it. I enjoyed even physics. I really liked physics too, but I didn't love it like I loved chemistry for some reason. So, um, how I like really got into chemistry was after high school. I went to community college because, um, you know, I like my parents couldn't afford to put me through school. My grades were okay in high school, but it's not like I got any scholarships or recognition. So I just went to community college because that's what I could afford to pay for. And I um everybody in my life at the time was kind of telling me like, "Oh, you're good at math, you're good at science. You should you know be a go to med school, be a doctor, be pre-med." So I was thinking, okay, I'll be pre-med. That makes sense. And and if you're pre-med, you got to take organic chemistry. And so I took general chemistry first, obviously. Thoroughly enjoyed it. It was like high school chemistry with extra stuff. And so I got through general chemistry, and then I had to take OChem because it's on the MCAT. If you're pre-med, you got to take it. And I was terrified of that class. I was terrified because it has this reputation of like, this is the class that doctors fail or whatever. And it has the reputation of being, this is the dream crusher class. This is the class that determines whether or not you get to live your dreams of being a doctor or not. And so I studied for that class harder than I'd ever studied before. For anything, I was just doing it all the time, every day. And I discovered two things. That when you literally 0 days off from OChem, always spend some time with it, reading, doing problems, prepping labs, do all that stuff. And I found that working as hard as I did, the class wasn't as hard as everyone said it was. And two, I actually loved it. And it exceeded how I would say that I loved chemistry in high school and I loved Gen Chem, but I loved organic chemistry. It was amazing. It was so cool that I had to do that thing. Like I loved it so much that became the thing I wanted to do. I didn't care about going to med school anymore. I just wanted to do chemistry, and so that's what kind of changed my trajectory, so to speak. Because after OChem, that's when I declared chemistry as my major. That's when, so I declared the major. When I transferred to UC Irvine, I got involved in undergrad research and then applied to graduate programs. And after graduating, after graduating, I started teaching at community colleges down in Southern California. Originally, that's where I'm originally from, and that's step by step how I got to this place. So for me, it really was OChem that did it. It was, I had most people take that class and it ruins their dreams of med school because they hate it. For me, it did the opposite. It ruined my dreams of med school because I loved it too much to not do that for the rest of my life. And right now I'm teaching general chemistry. Obviously, right? That's the class you're in. I have taught OChem in the past. Sometimes at FLC, I get to teach an organic chemistry lab section. It partially depends upon their need, and the other reality is I'm part-time. So the part-time professors kind of get... the full-time faculty get to teach the fun classes, right? OChem is fun, second semester Gen Chem is fun. And so they kind of get first dibs on those, and so the part-time faculty are kind of... We're kind of waiting our turn. So hopefully, eventually I'll be able to teach it again, because that is the class that I love more than anything else. So yeah, that was kind of my path. That's how I got into chemistry.